fundamental reinforcement learning method is policy gradients. Yeah? And I already said a few things about it in the introduction. Yeah? So policy gradients means gradient descent or ascent, depending what you want to do. Right? And that has a huge advantage. Gradient descent, we know what it does. Right? If you set the learning rates right, you're proof to converge to a local optimum. And that's one of the biggest advantages of policy gradients. And the second big advantage is that the bias you add in these methods is typically very small. So they get good results, but you need a lot of samples, high variance. Yeah, that's exactly the trade-off. Let me just remove this guy. Okay, doesn't want to, then let's do it like this. So we had this categorization of reinforcement learning algorithms, value-based is covered now. And the next one is policy, we call it sometimes differently. So policy optimization, policy search, policy gradient. Policy gradient is one specific type of policy optimization, but the most common one. Right? And actor critic would be the hybrid version of this. Right? So let's look at policy optimization now, right? Which is on this axis that we have also already seen. So it's more on the right here, isn't it? So it's on policy, which means can only use samples from the current policy. Which means it's sample inefficient, rather sample inefficient, but less bias. So, and that's why it yields state-of-the-art performance in many domains, especially if you have simulations of the task you want to have, and the simulation is rather fast, then sample complexity doesn't really worry you, and you just throw these algorithms on and they work. Yeah, and they're also much easier to use for continuous action spaces. So, because that's one of the core disadvantages as well of standard Q learning, we had to solve the maximum of the actions, isn't it? And if you have a continuous action space, that might be not so easy to solve, because you have to solve it for every state. For every state, you have an own optimization problem. And you don't have that for policy gradients. We'll see why. So the agenda for today is maybe the first part, not fully, but we look at policy gradients, how they are derived using the likelihood ratio trick, and look at baselines and the temporal structure of policy gradients, how we can exploit that. Yeah, then this is really annoying. Go away. Oh. Can I move it? Okay. So by policy optimization, so I already said a few reasons. So the last one would be the continuous action spaces. It's much easier to use that. And that often it is also easier to learn actually policies and to learn a Q function. It depends a little bit on the problem. But for example, for things like grasping in robotics, it's sometimes really easier to learn the policy, what the policy should do, except in difference to learn a function that says how good a certain configuration of my hand is, which is sometimes quite hard to do. So it really depends on the task, which kind of method does work better. So here we do have a comparison between policy optimization and value-based methods. What are the main property differences? So in policy optimization, we really optimize what we care about. And we care about the return. We optimize it. In value-based methods, we optimize the value function. And it should basically, if you want to have a good value function that has a low mean squared Bellman error. But in the end, this is an indirect way. And so in the end, I couldn't care less about the value function. If my policy is good, then that's okay for me, isn't it? So the value function is just an intermediate representation that is needed by these algorithms. But they don't directly optimize what I want to optimize. So it's an indirect optimization. And so that's conceptually, empirically, policy optimization methods are often much easier to tune. They are much faster in terms of computation time, and can learn more complex solutions because they almost add no bias to the policy optimization problem. So with value-based methods, I always have the bias from the Q function. Here, I don't have a Q function base. But they need much more samples. And on the right side, we have the value-based methods that are more sample efficient, but have all these problems with convergence guarantees and bias and something like that. And yeah, what people looked at in the last not quite 10 years, maybe 8, is such kind of benchmark tasks. You might have seen that if you look into reinforcement learning papers a lot. So it's simulations. You can use it to benchmark your algorithms. We'll see that in a lot of applications or a lot of papers. This standard simulator is actually still Motroco, which is a simulator now has been bought by DeepMind, and it's open source. So you see different examples like the hopper, the walker. So it's a planar scenario, so it can only jump forward, it cannot fall sideways. Half cheetah, the ant, the humanoid. Humanoid is actually already quite complex. But it's simulations, it's not very accurate. But in order to benchmark algorithms, it's a good thing. And basically, these are the kinds of tasks that we will look at. So, I mean, in the last 2 or 3 years, different simulators have been developed, like from NVIDIA, the ESAC simulator. That seems to be the new hot stuff now, because it's very, very fast and you can simulate on the GPU. But now there's a new Motroco version that can also do that. Okay, so the videos do work always. So here you see some policies, but more or less initial random policies, of these different tasks. So the humanoid on the right side is basically always falling down, and then the task is resetted. Okay, so policy gradient methods. As the name already suggests, it's a gradient method. Gradient means you compute the gradient vector of our objective. The objective is J, and J is really the expected return of the policy, no matter which state it is. So we want to get this return high. And policy gradient means a gradient update is you update your parameters in the direction of the gradient. Is that gradient ascent or gradient descent? What is that? If you look at this equation. Yeah. Ascent, because it's basically you go in the direction of the gradient. Why is it gradient ascent and not descent? Or why do you want to do gradient ascent? Yeah. We want to maximize, isn't it? Yeah. So usually when we talk about deep learning, it's gradient descent because you want to minimize the loss. Here it's a maximization problem. The only difference is the sign. Yeah. So, but before we talk about how to compute this gradient, maybe we should talk about how would the policy now look like. So now it's really we need an explicit representation of the policy, which means before we didn't need that. So we had the Q function, and the Q function already defined the policy implicitly. Always take the action with the optimal Q value. Now we have an explicit representation of the policy which means it's a neural network in most cases. The policy is a neural network. And you can, again, distinguish between two cases, discrete actions and continuous actions. For discrete actions, it's again, you can again actually say it's a classification problem. Given a state, I want to know which of my discrete actions I want to take. Classification. Softmax. Yes. Same thing. The softmax is giving me the probabilities for each action. Yeah. Sorry. If you would have different amount of possible actions in the network, what you would probably do is you know the maximum amount of actions, isn't it, for all states, and you would have a network that is the number of actions is this maximum amount, and then for some of the actions that are not valid, you would for this state not use the output basically, which means here you would sum over all the actions, isn't it? You would only take the subset. Yeah. Yeah. So what you would do is basically that if it's not valid, this probability is zero and set to zero, hard-coded set to zero. And the softmax is only defined on the remaining actions like this, hard-coded. So for discrete actions, it would look like that. For continuous actions, it's on the right side. It's usually Gaussian distribution. Because Gaussians, this is a more or less the only distribution in continuous spaces which is easy to handle. So we have to use a Gaussian. And Gaussian distribution, where the mean is defined by neural network, and sometimes also the variance is defined by neural network. Quite often the variance is a constant. It doesn't depend on the state. It's still learned, but it doesn't depend on the state. That's a standard case. What does the variance do of my Gaussian distribution? Why do we need this? Why do we want to have variance? Why don't I set it to zero? Yes. To explore. Well, I need exploration. That's why I have a variance here. I don't want to take the same action all the time. I don't learn. I need to explore. No? Yes. Okay. So let's have a look again at the goal of reinforcement learning, and we will write it slightly differently now. Because for this derivation, we need it slightly differently. So the goal of reinforcement learning is maximize the return. Again, the return is here. The only difference is now I've written it explicitly in a finite time horizon with until capital T, let's say 200. And the expectation here is now also written differently. It's not written over the policy as before. It's written over trajectories. What is it? What is a trajectory? It's basically a sequence of states and actions of size t. Trajectories of status. And for this sequence, I can compute the probability of this trajectory. So how likely is a certain trajectory that I see it? And then I can do this expectation. And that's exactly what this trajectory distribution here is telling us. How likely is a certain trajectory? So I sneaked in another symbol here, which I maybe have to told you here. Yes, here it's already defined. Theta. Theta is now the parameters of the policy. Before we had theta, which was parameters for a Q function. Now it's theta, parameters of the policy. Both are parameters of a neural network. But just to distinguish between policy and Q function. Theta are the parameters of the policy. And I want to find the parameters that of the policy, the theta, that maximize this return. And what I can observe as well is because the policy depends on theta. Here. Also, the trajectory distribution depends on theta. The policy decides on the actions, isn't it? And that's part of the trajectory. And the trajectory distribution can always be written like that. Why can it be written like that? Which property do we exploit here? Yes. Markov property. This is the Markov property. It's basically saying the probability of my trajectory is the probability of the first state. That doesn't depend on the future, isn't it? So the initial state times the probability of each transition. And the transitions, they only depend on the current state and action. And of course, the probability of choosing an action, which is the policy. And it's a product of all because I have to factor in all the transitions, isn't it? So all the time steps. And it's just really a different way to write the same thing. Expected return. But expectation is now going over the trajectories. It's the trajectory view of the objective. And so how would we now go about it? So we could now say, we are clever guys, isn't it? So we know how to approximate an expectation. We can just take samples of the trajectory distribution, which means I just run my policy on my system and I get trajectories. And then I compute the average of it, which is basically done here. That would be how good my policy currently is, the return, expected return of the policy. But the problem that you immediately see here, if I write down this average return, if I want to compute a gradient now, there is no theta anymore. So how should I get my gradient? If I derive that with respect to theta, this will be 0. Maybe not so useful. So because we completely neglected that the trajectories are samples from the distribution p theta, and that this distribution will change if I change theta. We have to account for that, isn't it? And that's basically how to do it. How we can compute the gradient in a better way. So we first have to realize, okay, this expectation is nothing more than that, isn't it? An expectation over the trajectory distribution over the return, which is now written here, abbreviated here as R of tau of the trajectory, is integral of the density, which is the trajectory distribution times the return. Definition of an expectation. Now I want to compute the gradient. This is our shorthand notation for the gradient. It's the Napler operator. So the same as dj of theta, d theta. Same thing. And so what I can always do is, if I have a derivative over there, for an integral it's again a little bit sloppy notation, but for most integrals I can do that. I can move the derivative inside. Because the integral is a linear operation. You can think of it, if I have a sum of different terms, I would also move the derivative inside the sum, isn't it? Because if I have f of x plus f of plus g of x derived by x, it's the first derivative plus the second derivative. So I can move that inside. So that's what I have here. But now what I end up with is an integral that is not an expectation anymore, because this is not a density, isn't it? It's a derivative of density, which is not a density. And then I cannot compute expectations I can compute with samplers, but this one is not an expectation. I cannot sample. But there is a nice trick that I can use, and it's called the log ratio trick, which basically comes from a very simple relation that we learned in high school, that the derivative of the log of f of x with respect to x is 1 over f of x times the derivative of f of x with respect to x. That we should know that, isn't it? This is a simple calculus. And now we can use this for our equation here. So here I have written down the same thing again, just not with f of x, but p of tau, or p theta of tau. And it's 1 over p theta of tau times the derivative of p theta. And now, if I look at it, so this is the bad guy. I want to get rid of him. So let's just reformulate this equation, and say this guy, I want to have this guy. I multiply with p of tau. Then I get the derivative of p of tau is p of tau times the derivative of log p of tau. Log ratio trick. And now I can just plug that in. And then I get, again, an integral. But now the good thing is this integral is an expectation. Why is it an expectation? Yes? There's a density and some function, exactly. Density and some function. Some function, again, depends on the density, but that doesn't matter. So this is a nice expectation. I can evaluate it by sampling from p of tau. And which basically leaves us to the part of computing this guy, the derivative of the log of the trajectory distribution. And that's, I think, the last slide for today. What you can see here, also no black magic if you think about it, but it's a lot of equations. It's basically, again, a basic property of the log. The log is your friend because it turns a product, which is often nasty to compute, into a sum. And we had a product, isn't it? We had, for the trajectory distribution, we had this huge product here over all the steps. And this is now a sum. That's just what the log does. Great. So we have the log of the probability of the trajectory distribution is the log of the initial state distribution plus the sum of all the logs of the policies plus the sum of all the logs of the transitions. And now the good thing actually is I want to know the derivative of this with respect to theta, isn't it? And all the things I don't know, I mean, I don't know this guy, so I could not compute that. But it doesn't depend on theta. This one also doesn't depend on theta. Only the policy does, And I know the policy. This is my neural network. I can compute derivatives. So which basically means I don't need to know the system dynamics, which would be this guy. I only need to know the derivative of the policies, sum them over all the time steps, and that's equivalent to the derivative of the trajectory distribution. And yeah, maybe just to finalize this, I lied, it was not this last slide, this is the last slide. We just put it together, which means we have now the derivative of the trajectory, which is here, the derivative of the policies, of the policy at every time step. Here, this is a return. And I said I can use sampling for this, so I can approximate it with a sum over my average over the samples, trajectory samples, and that's the first policy gradient algorithm. It's called reinforce. That has been invented around 25 years ago. Okay, and that's where we will continue from tomorrow. Thank you very much for coming, and we see each other tomorrow again.